Welcome back to Physics 142. In this video, I want to do a brief example about self-inductance and inductors, and specifically, I want to think about the amount of back EMF or the amount of self-EMF that different inductors are supplying to a circuit. All right, so in the last video, we learned that inductors are these circuit elements that oppose rapid change in a circuit, right? They have a specific amount of self-inductance, and their goal is to oppose rapid changes in a circuit. We realized we could define the inductance L using as the proportionality between current and the flux through an inductor. All right, if you have more current, you have more flux, and if you have more inductance, you get more flux. All right, and that means that if you want to know about the potential across that inductor, right, the EMF across that inductor, well, it depends on the inductance and on the change in the current. So to sort of understand this more, what I'd like you to do is sort of see if you can think through the following problem. All right, I encourage you to pause your video and see if you can work through this before I do, right? Sort of beat me to it, right? And what I want us to think about is I have, let's say I had 4 different inductors, all right? I'll have a 200 nanohenry one, a 100 nanohenry, a 400 nanohenry, and another 100 nanohenry, all right? So 4 different inductors, and I'm going to have different things happen to the current. So in scenario 1, I'm going to increase the current from 1 to 2 amps in half a second, all right? In scenario 2, we'll keep the current constant at 4 amps. Right? In scenario 3, we'll decrease the current from 2 to 1 amps in half a second. And in scenario 4, we'll increase the current from 0 to 4 amps in just a quarter second here. All right, so bigger change, less time. We'll see what happens. All right, and so we need to rank these. I'd like you to rank them from most opposition, all right, the most opposition to the least opposition, all right? So you might think, if we get a very negative answer, right, that means we're opposing, we're losing lots of EMF, all right? We'll rank that as top, all right? And if you get a really positive answer, that means you're actually supplying EMF, right? You're not opposing, you're actually helping, right? You're aiding what's going on. So, all right, so give you a chance to pause. And now let me dive into the solution. So we know that calculating the EMF, right? Calculating the EMF is minus L times di dt. All right, so in this first case, to do that, minus L, we do minus 200 nanohenries, right? Minus 200 nanohenries. And di dt, well, how are we going to do that? All right, how do we do di dt here? Well, it's just the change in current. So final current is 2 amps, and then we minus 1 amp. Right? And how long did that take? That takes half a second, right? So that's change in I over change in T, all right? That lets us calculate di dt, and I think if you calculate all that, I got that this, for number 1, maybe I'll write it over here, I got minus 0.4 microvolts, all right? As a result of that, right, this has to come out in volts, right? And so this was in nanohenries, and I ended up getting an answer that ultimately was in microvolts. All right, so we can do the same thing here, except where we start at 4 amps, we end at 4 amps, and so we know here that if we have constant current, we plug in a 0 here, and that means we have no EMF, right? So this is 0 microvolts, right? 0 there. Now, well, okay, what if we do this the other way? All right, now we're going from 2 to 1 amp in half a second. I guess I have more, a different inductor, right? So again, I'd plug in minus L di dt, right? And now I would have minus 400 nanohenries, but now I have 1 minus 2 amps, right? Because I end at 1, I start with 2 in half a second, all right? 0.5 seconds. And so if I do that, it's actually double the inductance, so I'm going to get double the answer, but opposite sign, right? So I end up getting plus 0.8 microvolts, all right? So that means here we're actually supplying current to the circuit, right? It's acting like a power supply, All right, and in this last case, we've got some different numbers. All right, so I could plug those in. I think I get minus 100 nanohenries times 4 minus 0 divided by 0.25. All right, and when you plug that all in, I get actually a much bigger number. I get minus 1.6 microvolts, right? It ends up being 4 times as large, and definitely opposed, right? It's opposed to this big increase of current. So I guess we say ultimately as a ranking, right? Number 4 is the most opposed, and then number 1, and then number 2, right? Number 2 is not very opposed, or 4, right? It likes the fact that it's steady. That's happy. And then number 3 is the least opposed, so much so that it's actually helping things out. It's actually providing some power. So hopefully this example helps you just think a little bit more about inductors and how they work.